400 million years ago, before dinosaurs, before flowers, before anything we'd recognize as modern life, a plant evolved a trick so effective that humans eventually built an entire civilization around it. It learned to store energy as pure sugar inside its own stem. One plant, one molecule. And today, that single evolutionary decision drives a global industry worth more than $40 billion. I'm Tom Marsh, and this is the story of how raw cane and a humble root vegetable become the white crystals sitting in your kitchen, and why the journey from field to factory is far more extraordinary than you might expect. Let's start with scale, because without it, nothing else quite lands. Brazil grows more than 700 million tons of sugarcane every year. That is more than any other country on Earth. Picture a field so wide you cannot see the end of it in any direction, stalks taller than a man, dense as a crowd, stretching to the horizon in every direction you turn. That is the starting point. And from that overwhelming abundance, the first decision a farmer makes is one of the most counterintuitive in all of agriculture. They set it on fire. Before the harvest officially begins, farmers across many producing regions burn those fields deliberately, not out of carelessness, out of logic. The sugarcane stalk, the part that matters, is surrounded by dried leaves, debris, and organic waste that would slow every machine downstream. Fire clears all of that in hours. It also drives out insects and reduces the sheer volume of unwanted material being transported to the mill, which cuts fuel costs on every truck in the chain. It is brutal and it is efficient, but it comes at a cost. The smoke is significant, the emissions are real, which is why burning is now strictly regulated in most producing regions, and where it is still permitted, farmers must work within tight windows defined by wind direction, air quality monitoring, and seasonal conditions. The industry knows this cannot be the long-term answer. And so modern green harvesting, cutting the cane fresh and unburned, is rapidly becoming the new standard. The machines that do this are worth pausing on because they are genuinely remarkable pieces of engineering. A modern sugarcane harvester moves through the rows and does several things simultaneously. Rotating blades cut the stalks cleanly at ground level close enough to the soil that the root system stays intact, allowing the plant to regenerate for future harvests without replanting. As the stalks feed into the machine, an internal separation system strips the leaves and tips away using powerful fans, and those unwanted parts are returned directly to the field. They fall behind the machine as a natural mulch layer that retains moisture and feeds the soil. The clean, sugar-rich stalk segments are chopped into short billets and loaded into a storage chamber at the rear. The throughput is difficult to fully picture. A single harvester can process between 80 and 120 tons of cane per hour. To put that in human terms, you would need dozens of workers with machetes working continuously to match what one machine does in 60 minutes. The moment the chamber is full, those billets transfer to waiting trucks at the field's edge. Speed matters here. Sugarcane begins losing its sugar content the moment it is cut. Enzymes start breaking the sucrose down almost immediately, so the window between field and mill is tight. Every hour of delay is lost sweetness, and lost sweetness is lost money. Now here is something that reframes how you think about the whole system. Sugarcane contains up to 16% natural sugar by weight. Compare that to most fruit, which sits below 10%, or grains like wheat and maize, which are a fraction of that. And it takes roughly 10 stalks of cane to produce a single 1 kilogram bag of refined white sugar. That ratio is the reason this plant became the foundation of a global commodity market. Its efficiency, relative to everything else humans tried, is essentially unmatched in the plant kingdom. At the mill, the cane goes through a wash. First, high-pressure water jets remove soil, sand, dust, and any surface contamination. This matters for equipment longevity as much as for hygiene. A stone or a clump of hardened earth entering a crusher under tons of pressure can cause serious mechanical damage. Once clean, the stalks pass through cutting machines that break them into smaller sections and then into the crushers themselves. Think of the crusher as a very powerful wringer. Heavy metal rollers press the cane continuously, forcing the juice out of the fibrous material in the same way you might wring water from a soaking cloth. The raw juice runs off and begins its journey toward becoming sugar. The dry fibrous material left behind, called bagasse, is a different story entirely, and we will come back to it, because what happens to bagasse is one of the more quietly impressive parts of this whole system. The raw juice that comes off the crusher is not clean. It contains fine fibers, dust, proteins, and various organic compounds that would ruin the final product if left in. The purification step uses something ancient and straightforward: lime. Calcium hydroxide, the same basic substance used in construction for millennia, is added to the juice. It reacts with the impurities, causing them to bind together and sink. The heavier particles settle out, and the clarified juice rises above them, noticeably lighter in color and already transformed in character. What follows is evaporation. The clarified juice moves into a multi-effect evaporator system, typically 3 to 5 connected chambers where water is progressively driven off by heat. Temperatures across the stages range from around 70 to 150 degrees Celsius depending on the pressure in each chamber. This is not a single boil, it is a carefully sequenced reduction, each stage using the steam from the previous one to heat the next, which recovers energy that would otherwise be wasted. By the end, the thin juice is thickened into a pale yellow syrup with a viscosity noticeably heavier than the liquid it started as. The next stage is crystallization, and this is where chemistry becomes almost alchemical to watch. Tiny seed crystals of sugar are introduced into the concentrated syrup. Think of them as templates. The dissolved sugar molecules in the syrup need something to organize around, and once they have it, they begin to grow. The mixture cools slowly over several hours, and as it does, more and more sucrose molecules leave the liquid and attach to the growing crystal surfaces. What was syrup becomes a slurry of crystals suspended in thick liquid. That thick liquid is molasses. It clings to the surface of every crystal and is inseparable from it at this stage. This is where the centrifuge comes in. The slurry is loaded into a spinning drum, essentially a very fast industrial washing machine, and the force of rotation throws the molasses outward through a fine screen while the crystals remain inside. What you have left, depending on how far the refining goes, is either raw brown sugar or refined white. The difference between them is not a matter of one being less processed in some vague sense. It is a precise chemical distinction. Raw brown sugar retains between 3 and 5% of its molasses content, which is where the caramel notes and the darker color come from. Refined white sugar is taken further dissolved again in hot water, filtered through activated carbon to strip the remaining color, then recrystallized until it reaches a purity of 99.9% sucrose. That is essentially the pure molecule itself, with nothing else along for the ride. The dried crystals move to an automated packaging line that operates in a sealed, hygienic environment. Electronic scales weigh exact portions. Heat-sealed polyethylene bags form continuously from film rolls. Metal detectors screen every package before it leaves the line. Batch codes and expiry dates are printed and the bags are packed into distribution cartons. The speed of modern packaging lines capable of processing hundreds of units per minute is one of those things that, once you have seen footage of it, permanently changes how you look at a supermarket shelf. Now, about the bagasse. The dry fibrous material left after crushing is not waste. In a well-run mill, virtually nothing is thrown away. Bagasse is collected and transported either by truck or through centralized pipe systems to specialist processing facilities. There it is washed under high-pressure water to remove residual impurities, then pressed or lightly dried to reduce its moisture content before the next stage. The processed fibers are milled to break down their structure, then cooked at high temperatures, sometimes with small amounts of natural binders like starch or recycled paper pulp to improve the material's consistency. The resulting slurry is pressed into preheated metal molds at temperatures between 160 and 200 degrees Celsius. The combination of heat and pressure drives out remaining moisture and fixes the material into whatever shape the mold describes: plates, cups, bowls, food containers, The surface is trimmed, edges are smoothed, and a water-resistant coating derived from biological or plant-based sources is applied so the finished product can hold hot food and liquids safely. These bagasse products can biodegrade in composting conditions within 60 to 90 days. The comparison that matters. Conventional plastic takes somewhere between 500 and 1,000 years to break down. That gap is not a minor difference in degree. It is a categorical difference in kind. Though it is worth being honest here, bagasse products need proper industrial composting conditions to break down at that rate. In a standard landfill, without the right temperature and microbial activity, they will take considerably longer. The technology is real. The infrastructure to make it fully effective is still catching up. Now let's move north and shift our raw material entirely. While Brazil and the tropical world run on cane, roughly 55% of the sugar consumed in the United States comes from a completely different plant, the sugar beet. It grows in California, Idaho, Michigan, Nebraska, and North Dakota climates that could not be more different from the Brazilian sugarcane belt, and it represents an entirely separate agricultural tradition with its own logic and its own machinery. Sugar beet is planted in spring, once the soil has warmed past the last frost risk. Fields are plowed first to loosen the earth, improve drainage, and turn over any residual weeds. Manure is worked into the soil to improve its water retention and organic content before the seeds go in. The planting itself uses automated precision seeders machines that place seeds at a controlled depth of 2 to 3 centimeters and a consistent spacing that balances root development against the practical need to harvest as much from each hectare as possible. Each seeder hopper can hold thousands of individual seeds. The geometry of the field, row by row, is established at this moment, and it will define every subsequent operation, from irrigation to harvesting, for the next 7 to 8 months. Irrigation in sugar beet country uses rotating arm systems, long pivot arms that sweep across circular fields, their built-in sprinklers distributing water uniformly across every plant in the arc. The system is automated. Rotation speed, timing, and volume are calibrated to soil conditions and growth stage. Too much water promotes disease. Too little stunts the beet and reduces its sugar concentration. Fertilization follows the same logic: nitrogen, phosphorus, and potassium applied at key developmental moments, timed to the plant's demand curve rather than to a fixed calendar. At harvest, 7 to 8 months after planting, specialized machines move through the rows in sequence. The first pass removes the leafy tops, cutting the foliage from the root cleanly. The second machine follows behind, excavating the beet from the soil with a precision digging mechanism designed to lift the root without fracturing it. Once lifted, the beet moves along a conveyor where a preliminary cleaning stage removes most of the adhering soil before the load transfers to a waiting truck. Modern beet harvesters can work across 12 rows simultaneously. The capacity this creates at the field level means that even large-scale operations can complete harvest before deteriorating autumn weather closes the window. Each hectare of sugar beet typically yields between 30 and 70 tons of root, depending on soil quality, weather through the season, and variety selection. Because trucks cannot drive across the harvested fields without damaging the soil structure, the beet is offloaded at the field edge using conveyor systems that bridge the gap to the road. From there, it goes to consolidation areas, large outdoor storage depots, where the raw beet waits in organized quantities before processing begins. The scale of these depots is striking. Mountains of beet, pale and earth-smudged, waiting for the next stage of their transformation. Inside the processing plant, the sequence mirrors sugarcane in structure but differs in detail. The beet arrives at automated wash systems where high-pressure water and rotating drum mechanisms remove surface dirt, stones, and debris. Optical sensors with cameras and scanning equipment then inspect each beet for size and quality. Damaged or undersized roots are sorted out before they enter the main processing line. Slicing comes next. The washed, inspected beets pass through cutting machines that produce thin strips called cassettes. The geometry here matters. For the same reason, a tea bag works better than a tea block. More surface area means faster, more complete extraction. The cassettes go into large extraction tanks filled with hot water at around 70 degrees Celsius, which dissolves the sucrose from the beet tissue without requiring any mechanical crushing. The sugar simply diffuses out of the cells into the water, and the resulting raw juice, high in sucrose, but not yet clean, is collected and moved on. Purification in beet processing uses milk of lime and carbon dioxide rather than the simple lime addition used in cane. The lime reacts with impurities and forms insoluble compounds that precipitate out. The carbon dioxide then reacts with the excess lime, removing it too. The result is filtered under high pressure to produce a cleaner juice, which then moves to evaporation towers, vacuum-assisted this time, to lower the boiling point and protect the sugar quality through the concentration process. Crystallization and centrifugation follow the same principles as cane. Seed crystals are introduced to the concentrated syrup, the mixture is cooled slowly, crystals grow, and the centrifuge separates them from the adhering molasses. The molasses from beet processing is repurposed. It becomes a raw material for other industries, including animal feed. The crystals go to drying equipment, where hot air reduces moisture content to specification, and from there to packaging. The finished product, whether it started its life in a Brazilian cane field or a North Dakota beet field, is chemically identical. Sucrose, refined to a purity that makes it functionally indistinguishable regardless of its origin. That fact that the molecule is the same whether it grew in a tropical grass stem or a temperate root vegetable says something interesting about how nature works. Evolution found the same solution twice, in completely different organisms, in completely different climates. The sugar beet and the sugarcane are not related in any meaningful botanical sense. They arrived at the same answer through entirely separate paths. And humans, following the logic of calories and chemistry rather than botany, industrialized both of them. When you look at what this system produces and what it wastes, or more precisely, what it no longer wastes, a picture emerges that is more sophisticated than the commodity label suggests. A mill that runs well turns the juice into sugar, the bagasse into fuel and packaging material, the molasses into feed and fermentation substrates, and the heat from combustion back into the steam that drives the evaporators. The circle is not quite closed, but it is far closer than it appears from the outside. There are more stories like this than you'd think. The hidden complexity inside the ordinary, the engineering ingenuity embedded in things we take for granted, and the ecological consequences of choices made at industrial scale. I have plenty more to tell you. If you have thoughts on where the sugar industry should go next, more renewable packaging, closed-loop processing, changes to agricultural practice, leave them below. And if this kind of deep dive into how the world actually works is something you want more of, share it with someone who would find it as surprising as you did, and subscribe so you don't miss what's coming. I'm Tom Marsh. Thanks for watching.